right, welcome to the Quiz 9 solutions. So let's go ahead and jump into this. So for question 1, we are being asked to show where the person on the swing is going to be moving the fastest. She is undergoing simple harmonic motion. So this is the simple harmonic motion of a pendulum. So what happens when you're on a swing is at point A and E, you are changing directions, right? You were going, in the case of A, you were going to the upper left, and now you're going to start moving to the right. So what that's going to result in is the fact that you are stopping to change direction. So A and E cannot be the answer as you are stopped. And you have to get from point A to point E somehow, indicating that at some point you do have a speed value. So that means A, E, and F are not possible answers. At B and D, you are continuing, you are going in one or the other direction. In the case of where the girl is now, you're going from A to B to C to D to E. So from A to B, you would have to be speeding up. You're going from 0 to some speed value, but from D to E, you are slowing down. You're going from some speed value to a 0 value. And if you do it the opposite direction, or let's say you're going from E to A, this would indicate at D you're speeding up and at B you're slowing down. So they're going to have the same behavior. At point C, this can kind of be thought of as our equilibrium position, where if there was no tangent gravitational force, C would be where our pendulum would want to sit. So this means that C is going to be a location where we are at our lowest point for gravity. Right? It's physically going to be when you are the lowest. There's no angle for the swing. So this means our gravitational potential energy is going to be 0 if we set our gravitational potential energy to be equal to the lowest point on the swing. That means we only have kinetic energy at point C. So B and D are not going to be answers because you are either speeding up or slowing down depending on the direction. Because you are still speeding up or you have begun slowing down, there can't be the fastest location. C is. So C is going to be our answer for this one. Another way you can think about it is when we talked about the horizontal simple harmonic oscillator. So at negative amplitude and positive amplitude, we only had kinetic energy. And when we were at equilibrium, we had the case where we only had kinetic energy, so we had our maximum velocity. Even though the pendulum is not moving in the same exact way, or we're not just moving in the x direction, we're moving in x and y for the pendulum, the same general behaviors hold true. So we're going back and forth. A and E act as our amplitudes, our maximum displacement values. C is our equilibrium, so that means we have to be going the fastest at that point. Number 2, sound is a transverse wave. A transverse wave is one where the medium moves up and down, but the wave moves to the perpendicular direction. This is, we talked about it for something on a string. This is also light. Sound is not a transverse wave, it is a longitudinal wave, so the answer is going to be false for that. So number 3, you could do this in a couple of different ways, but we are given an index of refraction n as 1.55. The speed of light c is 3 times 10 to the 8 meters per second. And we are being asked in part A to find the speed of light as it moves through the amethyst. So we have an equation for the index of refraction. It's C over V. So we'll just need to rearrange that to have V is equal to C divided by N. In B, there are two methods in which we can go through and solve. Now be aware we are solving for the wavelength in this situation, so we need to make sure that we are accounting for what we're actually solving for. And if we look at the wavelength that is given for our Blu-ray laser, it's in nanometers, so we should convert that into meters, so 405 times 10 to the negative 9 meters, or 4.05 times 10 to the negative 7 meters. Either way, again, these two numbers are the same thing. So we could either use directly the equation that is given in the possibly useful equation. So we have the wavelength in the material being equal to the wavelength in a vacuum, divided by N. Or if we want to, we could find the frequency, which is going to be equal to the speed of light divided by the wavelength, and then plug that into the equation. V is equal to frequency times wavelength. So this would be a vacuum material would be equal to V divided by F. So either of these methods works out. Both are going to be on the Word document version or the PDF version of the solution that is all typed out. I am just going to be solving it using the easy method because why do two steps when I can do one? So let's go ahead and let's solve for part A. So for part A, again, we are just solving for the speed of light in our amethyst. So we're going to have 3 times 10 to the 8 meters per second divided by the index of refraction of amethyst, which is 1.55. Taking this and plugging it into a calculator, I got 1.9355 times 10 to the 8 meters per second. So it's still extremely fast, but we have reduced our speed. So that means that the speed of light in amethyst is about 1.9 times, speed to, so that's positive 8, to the 8 meters per second. So it's still way faster than the human mind is able to comprehend. So we're not going to notice a difference, but if you were something that was able to track an individual photon, you would notice this difference. So for part B, we are taking our wavelength and we want to find the wavelength in the material. And we're just going to take the wavelength, it's the speed of light divided by the wavelength. Or sorry, no, it's the wavelength divided by the index of refraction. So that's going to be, I'm going to keep it in nanometers because usually we give our wavelength in nanometers. So 405 nanometers divided by 1.55. Taking that and plugging it in, I got 261.29 nanometers. So that means that the wavelength in the material is going to be 2.6 times 10 to the negative 7 meters, or 260 nanometers. Either of these answers works out. It's just going to depend on what you ended up doing. If you did the other method where you, let's just do it. Let's just do the other method. So this one, we are going to be finding the frequency of our wavelength. So we're starting with C is equal to frequency times wavelength. Going to calculate the frequency of our Blu-ray laser in vacuum. The reason we're going to want to calculate this is the frequency in vacuum is going to be the same as the frequency inside of our amethyst. This has to do with the fact that the vacuum laser is the source for our wave inside the amethyst. So because there's no delay between light, like the wave, if the crest of the wave is hitting the amethyst isn't going to randomly be at the trough or at 0. It's going to also be at the crest. So the frequency is the same in both. So we're going to have speed of light divided by wavelength. So we'll have 3 times 10 to the 8 meters per second. Here's where we need to make sure that we have our value in meters for wavelength, because our speed of light is in meters per second. If you want to take meters per second and take that and turn it into nanometers per second, you're welcome to do so. You're going to be dealing with some pretty big powers, but it doesn't really matter. Works out the same way. So plugging this in, I got 7.4074 times 10 to the 14 hertz. So this is the frequency of our Blu-ray laser in both vacuum and in the amethyst. So now what we're going to use is the speed is equal to frequency times wavelength, where this is the speed of light in our amethyst. The wavelength is our wavelength in the material. And the frequency is again the same as the vacuum. So that means that when we rearrange this, we're going to have wavelength. Technically it's the material, so I'm going to put matte just so I know it's not the same as what I was given. It's going to be equal to the speed that I solved for in part A divided by the frequency that I just solved for. So I'm going to make sure I use extra sig figs in my answer. So 1.9355 times 10 to the 8 meters per second divided by the frequency that I just solved for. So taking those two and plugging it in, I ended up getting 6.2129 times 10 to the negative 7 meters. Oh, sorry, it's 2.6, not 6.2. So that's 2.6 times 10 to the negative 7 meters. Oops. Sorry, this is a 3 sig problem. I realized I didn't use 3 sig figs in literally another part, and I should have. We were given 3 for both our wavelength and our index of refraction, which should indicate that we should have 3. The speed of light, C, does not influence our number of SI units because it is a constant, or sorry, not our number of SI units, our number of sig figs, because it's a constant. We're not supposed to let that influence us. But clearly mentally I have. So we're going to have 2.61 times 10 to the negative 7 meters, or 261 nanometers. So it's the same answer. I've just gone through and done 2 steps instead of doing it in 1. All right, so that's going to wrap it up for this the solution. If you have any questions, let me know.